Hello students, let us begin with the next topic, classification of organic compounds. Okay, so here you just have a look at the table. You need not take it down in your copy, just try to understand because classification will never be asked to draw during exam. Just you need to know what are the terms. So organic compounds, they are broadly classified as into two types, acyclic and cyclic. By acyclic we mean the open chain structures, and by cyclic or closed ring structures you can understand the first carbon will be linked to the last carbon also. Now in open chain structure we have the classification primary, secondary, tertiary that we will do later. But under the closed ring structures you can see there are two types, homocyclic, also called carbocyclic, and heterocyclic. By homocyclic we mean when we form the ring, all the members of the ring are carbon, and in heterocyclic we mean in the ring at least one atom, one of the members of the ring, is not carbon. Such compounds are called heterocyclic compounds. Now homocyclic as well as heterocyclic both can be classified as elecyclic and aromatic. Okay, now we'll discuss each one of them. And aromatic is further classified into benzenoid and non-benzenoid form. Now let us try to take up and understand each of these different types. So first we take acyclic or open chain structure. You can see here we have two carbons linked to one another, and we know this name of this compound is ethane. Then we have taken one more molecule where we have three carbons in the longest chain, and in the central carbon we have a branch, and the branched carbon is also containing a CH3. Name of this is 2-methyl propane as per IUPAC rule, and common name is isobutane. When we say iso, when two CH3 groups are attached to one carbon, such system is called iso. Okay, and it is a common name system. And since here altogether we have four carbons, that's why we call it butane, and all being single bond we call it butane. Okay, so isobutane. Naming you will learn slowly. The next compound is containing a functional group. You can see here. Here we have two carbon, and this is CHO group called aldehyde group. Common name they have given here. Common name is acetaldehyde. IUPAC name will be ethanol. Then we have one more example here. This contains COOH group. COOH group is carboxylic acid group, as all of you know. The common name is acetic acid. IUPAC name is ethanoic acid. So they all come under the open chain structure. This is without functional group, this is without functional group but branch, and these are with functional groups. So doesn't matter whether the compound is having functional group or not, as long as the two ends are not linked to one another, they are called open chain structures. Then we move to acyclic structures or closed ring structures. Sorry, elecyclic or closed ring. Now in elecyclic what happens? You can see any one of these carbons, this is a bond line structure. Any one of these carbons can be considered as the first carbon, and you can see the first carbon linked to the second is linked to the third, and third is again linked to the first. So when the first and the last member is linked to one another, such a system is called elecyclic structure. So name of this is cyclopropane. Why cyclopropane? Cyclic, that's why cyclo. There are three carbons, that's why prop. All the bonds being single, that's why ane. So name of this is cyclopropane. Similarly, the next compound, this one, you can see here 1, 2, 3, 4, 5 and 6 carbons are there, and any one carbon can be considered as the first carbon here. So first carbon is linked to second, second is linked to third, third is linked to fourth, fourth is linked to fifth, fifth is linked to sixth, and the sixth is again linked to the first. So it is a cyclic compound, and name of this compound is cyclo because it is cyclic. Since there are 6 carbon, so hex. All the bonds are single bond, so ane. Name of this compound is cyclohexane. Then we have an alkene. This is also having a 6 carbon ring, and with a double bond. Okay, so we know alkenes are ended with ene. So name of this is cyclohexene. Let's check the difference between the two. This was cyclohexane and this is cyclohexene. Okay, so these were all example of homocyclic alicyclic compound. Now next molecule you see here, it is a 5-membered ring structure, but one of the members is not carbon, it is oxygen. So it comes under heterocyclic alicyclic compound. Name of this compound is Tetrahydrofuran. Okay, you have to remember this. In short, we call it THF. In your higher studies, you will encounter this molecule quite often. So since these examples are not very common, I would suggest that you should try to remember these examples or by heart the names. Then we have aromatic compounds. As the name suggests, aromatic compounds, they have aroma. That means they have smell. Okay. But looking at the compound, how would you know whether they have smell or not? Because we are not experiencing them directly. So in the next topic, in the next chapter rather, in the chapter hydrocarbon, we will learn how to know whether a given compound is aromatic or not by looking at the structure. Anyway, for the time being, you just accept that all these compounds, they are ring structures. Mostly they have alternate double bonds. Okay, you can see here we have a double bond, then single, then double, again single, then double, then single. So usually they have a benzene-like structure. Those who have a benzene-like structure, they are called benzenoid aromatic compounds. So this one is benzene, we all know, C6H6. Then we have benzene with a NH2. So it is C6H5NH2. Earlier also we have done the resonance for this. Name of this compound is aniline. Then this is a very well-known compound which most of us use at home. You can see there are two benzene rings fused together, and this is the commonly used naphthalene. I think all of you know what naphthalene is. The white balls which we get in the market with smell. Okay, and they are usually used in the cupboards to protect your clothes from pests, and also we use them in toilets. Then another compound which is also aromatic, you can see in this also we have alternate double bonds, but it doesn't look like benzene because it is a 7-membered ring. It is not a 6-membered ring like benzene, but it is aromatic. Okay, name of this is Tropolon. I want you to remember this structure also, because in the exam if they ask you to write down a non-benzenoid compound, you may not recollect all of a sudden. So try to remember this example. It is a 7-membered ring with alternate double bonds, and there is a C double bond O. Next we move to heterocyclic aromatic compounds. Okay, so as you can see in all these structures, one of the members is not carbon. Here we have oxygen with alternate double bonds. Here we have sulfur with alternate double bonds. These two structures are very similar, 5-membered ring with alternate double bonds, and oxygen and sulfur as the members, heteroatoms. And this is a 6-membered ring just like benzene, but one of the members is nitrogen. So they are all heterocyclic aromatic compounds. You should know their names. They are mostly known by their common names. This is called furan. You can see this one and this one. They are very similar. Okay, this one and this one. They're very similar. Their names are also similar. Here we have two double bonds. Here we have two double bonds, but here we don't have double bonds. So name of this is tetrahydrofuran, and name of the other one is simply furan. All right. Then the next compound is called thiophene. The word thio is very much associated with sulfur. So quite often you can see the compounds bearing sulfur can be named as thio. Then this is pyridine. Pyridine you have encountered in class 10 if you remember. In alcohols, pyridine is used as a smelling agent to prevent misuse of alcohol for drinking. You must have done it in class 10. Okay, and I don't expect you to remember anyway. So with this we come to the end of the classification part. Then I want you to write down only the definition of functional group. No need to write the whole thing. Functional group is the functional group, as the name suggests, you can understand. Presence of certain groups will decide the function or the property of the compound. Such groups are called functional groups. So you may write till here. The functional group may be defined as the atom or group of atoms joined in a specific manner which is responsible for characteristic chemical properties of the compound. Till here you may write. And you can include one or two examples like OH, CHO, COH, whatever example you want, you may write. Then we move to the next definition, homologous series. Homologous series, each functional group having a family. As you know, each functional group can be represented by a general formula. Say for example, alkane. Alkane has a general formula CN H2 N plus 2, where the value of N may vary from 1 to any number. Now if you keep on replacing N by 1, 2, 3, 4, we get series of compounds. Yes, if we have N to be 1, then we get CH4, that is called methane. If we put N equal to 2, we get C2H6, that is ethane. So if we keep on replacing the value of N by 1, 2, 3, 4, we get a series of compounds and they form a series called homologous series. So this way, each functional group will have their own series. And the interesting part of this series is all the compounds of the same series will have same chemical property. Only their physical properties will be different. Physical property means molar mass, boiling point, freezing point, all those properties will be different. So how much you need to write here? You can see it is already marked. A group or series of compounds which containing a characteristic functional group forms a homologous series and the members of the series are called homologues. Then you can please include this. The successive members, okay, the members of a homologous series can be represented by a general formula and the successive members differ from each other by a CH2 group. You may write till here. So the definitions should start from here and from here till here. Okay. Then the nomenclature we are not doing for the time being. We will be doing it later together as we encounter the molecules. We will be talking about the rules, but definitely we'll do something. But for the time being, you just ignore this part. Then we move to a very important topic, isomerism and isomers. Iso. The word iso. What does it mean? Iso means same. Okay. Probably you have heard the word iso first time in your life when you did isosceles triangle in geometry. So in isosceles triangle, what was the definition of isosceles triangle? A triangle which has two sides equal in size. Such triangles are called isosceles triangle. So in chemistry, you will encounter the term iso quite often. You have already heard isotopes, isomers, isobars. Now you are encountering isomers. So what is the definition? Compounds having same molecular formula but different structural formula and different properties are called isomers, and the phenomenon is called isomerism. Now isomerism has a broad classification. Broadly, isomers of two types. One is structural, another is stereo. In your syllabus, you need to do mostly structural. Stereo, very little you have to do. Now, as the name suggests, structural isomerism, you can understand we are comparing two compounds which have same molecular formula, but there will be some difference in their structures. In stereoisomerism, the compounds will have same molecular formula, same structural formula, but when they're viewed from space, then they appear differently. Okay, so those are stereoisomers. So stereoisomerism we'll talk later. First, let us try to understand the different types of structural isomers. The structural isomers are chain isomers, position isomers, functional isomers, and lastly metamerism. The first three are easy to predict. The last one is little difficult for you to understand or to predict or to guess. Okay, so let us try to understand one by one. Chain isomerism, as the name suggests, the two compounds, two or more, okay, two or more compounds, they have same molecular formula, but their chain lengths are different. Say for example, if we take C4H10 as the molecular formula, one of the possible structures is CH3, CH2, CH2, CH3. So here you can see we have made a carbon chain of 4. Name of this compound is butane by IUPAC system. But because there are 4 carbon, ane because all the bonds are single bond. According to common name system, it is called N-butane, where N stands for normal, which means straight chain, no branches. Okay. So we got one molecule. Looking at one molecule, we cannot show the isomerism. So the other possible structure is we make a carbon chain of 3 and the fourth carbon should not be in the terminals. That means not in the first and the last. The fourth carbon should be somewhere in the center. So in the center we have only one carbon, so the fourth carbon is linked here. And when you write the branch, make sure the line which represents the bond is linking carbon and carbon, not like this, okay, which doesn't make any sense whether it is linked to carbon or hydrogen. So when you write, make sure that it is linked to C. This must be taken very seriously. Now how do you name this? Name of this compound will be, name of this compound will be 2. At 2 position we have a CH3 group, and the name of CH3 group is methyl group. So name of this is 2-methyl propane. Now remember, methyl propane should be a single word, and between number and name there should be always a hyphen. Okay, between number and name there should be always a hyphen. So name of this is 2-methyl propane, commonly called isobutane. One more example I have taken here, C5H12. Okay, before that, so in what way the two compounds they differ? You can see the two compounds they differ by, here we have the carbon chain of 4 and here we have a carbon chain of 3, but the molecular formula is same. So you can understand these two compounds are chain isomers. So let us try to understand chain isomers with one more example. C5H12. So this is the molecular formula. One of the possible structures is all the 5 carbons are put as a straight chain, and to satisfy the valencies of carbon you put the hydrogens. So the first and the last one will be always CH3, and in the middle it will be always CH2. So name of this is pentane. Why is it pentane? Pent because there are 5 carbons and there are all single bonds, so it belongs to alkane family, so it is pentane, and the common name is N-pentane, normal pentane. The next example under the same category, you can see now we have made a carbon chain of 4, and the 5th carbon, as I told earlier, it cannot go to the first and the last, we have put it in the second carbon. And while numbering the carbon, you have to take care, it should not be 1, 2, 3, 4. Because if I number from right to left, then the carbon containing this CH3 get position 3. But when I number it this way, the carbon bearing this CH3 get position 1. So we should always assign lowest possible number to the substituent. This is called lowest locant rule. Okay. So name of this compound is 2-methyl butane. So if you compare the name, you can see this was having a word root pent and this is having a word root but. So this is having 5 carbon as the longest chain and this is having 4 carbon as the longest chain. So they are chain isomers. I'm not sure whether all of you know or not. If you have 1 carbon, then it is called meth. If you have 2 carbon, then it is called eth. If you have 3 carbon, then it is called prop. When you have 4 carbon, we call it but, not but. Okay, the spelling is but the pronunciation is but. Then if you have 5 carbon, it is called pent. If you have 6 carbon, it is called hex. If you have 7 carbon, then it is called hept. If you have 8 carbon, then it is called oct. Okay, there are 8 carbon, then it is called oct. If you have 9 carbons in the longest chain, then it is called non. And if you have 10 carbons, it is called dec. We don't need so many till dec also, we don't need. Maximum till oct only we use, that also very rarely. Now you must know that organic compounds have 3 parts in their names. The first part is called prefix, second part is called word root, and the third part is called suffix. Okay, prefix. Usually the straight chain compounds don't have prefix. Anything which is not part of the chain, such as this CH3, that should be named first, and that comes under prefix. Okay, then what is word root? Word root tells you the maximum number of carbon present in the longest chain, that is word root. And suffix tells you the family to which it belongs. Okay, so this is an alkane family, so the suffix is ane. Both the cases the suffix is ane. Now what kind of isomerism is possessed between the two compounds 1 and 2? Since they differ in chain length, they are chain isomers. But you see, with the same compound we have one more possible structure, and that is with 3 carbon as the longest chain. So we make a carbon chain of 3, and the fourth and the fifth one we put as branches. Okay, so name of this become 2,2 dimethyl propane. Why is it 2,2 dimethyl propane? You see, in the 2 position we have 2 CH3s, so 2 we have to write twice, and since both the groups are methyl group, we write dimethyl, so this part is prefix. Then we have the longest chain of 3 carbon, so for this we write prop, and since all the bonds out here are single bond, the suffix is ane, so 2,2 dimethyl propane. According to common name system, it is called neopentane. When we say something to be neo, when one carbon is attached to 4 other carbons, then we call it neo. If one carbon is attached to 3 carbons, then we call it tertiary. If one carbon is attached to 2 carbons, then we call it secondary. You will find it in the textbook also, and later on we'll discuss again. Alright, so the next type of isomers which we have is position isomers. So you can understand the 2 compounds will have 2 or more, remember always. It should be minimum 2, maximum no limit. When 2 or more compounds having same molecular formula, but they differ in the position of a particular substituent or a functional group, then they are called position isomers. Say for example, I have taken a molecular formula C3H8O. Looking at the molecular formula, we don't know what is the functional group, so I have chosen OH as the functional group. So there are 3 carbon. The first structure we have all the 3 carbons in the chain. In the second also we have all the 3 carbons in the chain. Okay, 1, 2 and 3. But in what way they differ? The OH group, that is the hydroxyl group or the alcoholic group, in the first compound is attached to carbon 1. Whereas in the second compound, OH is attached to carbon 2. So you see, the position of OH in the 2 carbons are different, though the chain length in both are same. So they are position isomers. Now how do I name them? The compound containing OH are ended with the suffix ol. So from the word alcohol. Okay, so this one propan 1-ol or N-propyl alcohol according to common name system, and this will be propan 2-ol or isopropyl alcohol. Iso because again 2 CH3s are attached to 1 carbon, that's why iso. So in what way they differ? They differ in the position of the OH group, that's why they are position isomers. One more example we can take. You can see here I have taken an alkane, okay, having 6 carbons. So here I have 5 carbons in the longest chain, and the 6th carbon I have put in carbon 3. Another structure I have taken where 5 carbons we have taken in the longest chain, but the 6th carbon we have attached to carbon 2. 1, 2, 3, 4, 5. So name of this is 3-methyl pentane, and name of this is 2-methyl pentane. So you can see in what way they differ. Here the position of the methyl group is 3, and here the position of the methyl group is 2. So they are position isomers. The next isomerism is functional isomerism. So as you can understand the name, functional isomerism means compounds having same molecular formula but they have different functional group. So we have taken an example C3H6O. So you can see we have written CH3, CH2, CHO. If you count, it will be C3H6O. And the functional group taken out here is CHO, which is known as aldehyde group. So here we have 3 carbon, all in a straight chain, so no prefix. So name of this is propan, and name of aldehydes are ended with L from the word aldehyde. So name of this is propan L. Now with the same molecular formula, we have written another structure CH3 C double bond O CH3. By the way, here also that O is doubly bonded O. Okay. So here the functional group is called ketone, and name of this is propanone. Prop because there are 3 carbons, and ketones are ended with -one. So name of this is propanone. Okay. So the functional groups are different. One is aldehyde, the other is ketone. So they are again functional isomers. Another example under the same category, you see, we have taken C2H6O, and with this we have 2 possible structures, CH3O CH3, CH3CH2OH. Here you see the functional group is alcohol OH, and here the functional group is ether. What is the difference between ether and alcohol? In ether we have O, and on both sides we should have carbon. And in alcohol we have O singly bonded. One side we should have carbon, the other side we should have H. That is how the ether and alcoholic group differ. Okay. So since the functional groups are different, so they are functional isomers. Their molecular formula is same. Name of this is methoxymethane by IUPAC system, and this is ethanol. The common name of this is dimethyl ether, and common name for this one is ethyl alcohol. Lastly, we come to metamers, metamerism. Metamerism, it arises due to, as I said earlier, metamerism is something new to you and difficult to predict from the name. Metamerism is difference in the distribution of alkyl group or distribution of carbon across a functional group. You see, here I have taken ether. Very few functional groups exhibit metamerism. Okay, so here we have taken ether, and we have taken altogether 4 carbons. But how is the distribution? Here we see on one side of oxygen we have taken 1 carbon, on the other side we have taken 3. Total is 4. And in the other molecule, on both sides we have taken 2 carbons. So the distribution of carbon across oxygen is different in the 2 molecules. Such compounds are called metamers. Okay. So name of the first one is 1-methoxypropane, and the second one is ethoxyethane. Name of ethers, it is better if we learn in the class. It is a little difficult to understand, but in class 12 we have to do it in detail. So we shall be doing it there. So with this I stop today's class. Stereoisomerism I'll take up in the next class. Little bit. Thank you.